Very good. All right, and I'll get started. And just please jump in if for some reason in the midst of this people can't hear me correctly. So I want to talk today about both new science and old history from beneath Greenland's ice. And I really want to focus on the power of sampling at the bed of an ice sheet rather than at the surface or within an ice sheet. Let's see if I can get my slides to advance. I'm going to start with a little bit of the science, then I'm going to duck off to the history for a bit, and then come back and finish with the science. Um, so what you see here is a photograph that we took looking down the microscope on the first day that we found fossils in the subice material from Camp Century. And today, of course, you can see Camp Century is the white dot up here in the corner. GISP-2 is the red dot in the center of the Greenland ice sheet. And this article, published in 2021 by Drew Christ, who is a postdoc on this project, provided the data from our initial work on the subice material at Camp Century. And it showed that there was a record of vegetation preserved beneath the ice at Camp Century. And it also gave some of the initial data of the chronology for that sediment. But this year, we finished our work on the material from the GISP-2 core. There's only about 8 centimeters of till in the GISP-2 subice core. The rest of it is rock. And in that core, we also found an assemblage of fossils. And this is a photograph of those fossils, including soil fungus, if you can see my pointer on here, a poppy seed here, and some spike moss megaspores shown here in brown. So now we had not only a frozen ecosystem from Camp Century, but we had a frozen ecosystem from the center of the ice sheet. And that's really important because when Camp Century deglaciates, modeling I'll talk about a little bit later mandates at least 1.5 meters of sea level rise. But when Summit at GISP-2 deglaciates, probably 95% of the ice sheet is gone. So we now have evidence from beneath the ice sheet that goes along with the cosmogenic nuclide evidence of Schaefer et al. From 2016 that the ice has been gone at Summit and it was replaced with a tundra ecosystem. And that's this paper here, brief report in PNAS this summer. There's a lot of other material coming out about Camp Century now. We have a large, almost 40-person working group. The first two papers I've just shown here, if people are interested, this one came out in the cryosphere just a couple weeks ago. It's a beast, is the best way to put it. It's our taking apart of the 28 samples in the subice core that remain extant at Camp Century. So it's an awful lot of detail and data and methods. And then following that, there are going to be a series of papers from the people working on the project. The first one is now in review. And this one is a characterization at various scales of the geochemistry and the physical properties of that core. And I'm also going to talk today a good bit about the book that I've been working on for 3 years, which came out in August, which is a history of exploration on the Greenland ice sheet, an environmental history, a history of Camp Century and the drilling there, and then the last chapter is really about the implications of that for us all. And this is not a science book so much as it's a popular book introducing the science to the broader community. So let's go back in history a little bit and go back to the Wegener's German expedition in the winter of 1930, 1931, which established 3 camps on the ice sheet. And the reason I go back to this is really the beginning of snow and ice stratigraphy as well as subice living. And there was a camp on the west coast of the island, a camp on the east coast, and then Ysmita in the center at the summit in southern Greenland. This is actually the last known photograph of Wegener before he left that camp, very late in the fall with very little daylight, to try to get back to the coast. And he never made it. But his team left an amazing a set of films of this expedition, which I'll play one of these now just to give you an idea of what they faced in the 1930s, but also how they were looking ahead. So here they are at the ice margin. Obviously, they had men carrying things, equipment up onto the ice across a very steep margin. But the other thing that they did, which was a first for Arctic travel, was they used mechanized transport. And their mechanized transport involved these snowplanes that had large pusher motors on the back. There's one of them there, or also called aero sleds. And they'd have a big propeller, which isn't installed on this one yet. And then if the snow surface was smooth, they had long skis on the bottom and they could go quickly across the snow surface. Of course, these were not easy things to get up onto the ice. And so a number of draft horses here, men, they're dragging this thing up. Here they are again, at the ice margin trying to get these things up. They had a winch. And you can see how steep the grade was that they're trying to pull these large contraptions up. But once they got up to the top, they put them together and they worked. And they allowed them in the right snow conditions to move very quickly over the ice. This is important because it presumably was an inspiration to the US military 10, 20 years later to mechanize transport across the ice. But the other thing that happened in 1930, 1931 was that three men spent the winter on the top of the ice sheet in this camp. The surface is rather modest here, a small tower for which they could have some shelter to take weather observations, a former weather station when they could get that far. But underneath a series of tunnels they dug in the snow. One was a bunk room and a cooking place. Another was a depot. And three men survived, I suppose not comfortably, but survived at Summit, Greenland in the winter of 1930, 1931. And these, you can see their living quarters here. Most of the pictures you see of them, they're either halfway or all the way in their sleeping bags, sleeping on snow benches. But the temperatures here were actually quite mild at the top of this little snow cave or large snow cave that they'd built. The temperature was not at the freezing point, but was in the 20-degree Fahrenheit range. It was much colder at the floor as it stratified thermally. But the real advance that happened here was that they dug a set of essentially stairs into the ice, the firn, and then a vertical shaft below that, and they sampled their way down. And as they sampled, and this is Ernst Sorga, who's cutting a block for density measurement here in their science trench. As they sampled, they measured density. And the surface snow was density or surface firn 0.3, 0.35, and you can see the density increasing as you go down. And not only did they sample density, but by doing this, they could see annual layers. They could see summer layers and winter layers. And so established really for the first time a snow stratigraphy down almost 15 meters. That took them back from 1930 back to 1910. And so this really laid the groundwork for the fact that snow and ice and firn could preserve a stratigraphy of what had happened in the past. Skip forward about a decade to World War II, and the US military became quite interested in Greenland, mostly because their airplanes that they were trying to get to the United Kingdom, to Great Britain at the time, simply couldn't fly across the Atlantic. Most of the airplanes didn't have the range to do that. They didn't want to put them on ships because of the U-boats that were prowling the North Atlantic. So they flew them in a series of hops from northern Maine and Presque Isle to Goose Bay to one of two bases in Greenland, onto Iceland, and then to Scotland, and into the European theater of war. But the problem with this routing was that the weather in Greenland wasn't particularly good, wasn't well forecast. Um, and the planes had a bad habit, even though they were flying close to this great circle route, of falling out of the sky and onto the ice. And that necessitated rescues. And so the Coast Guard, members of the Air Force were set to rescue people, but that didn't tend to go very well. Again, because they had poor weather and they had poor equipment. But one of the things they did find was that the Nazis were quite interested in the weather in Greenland and actually had established a set of bases along East Greenland. And in fact, the Coast Guard captured the weathermen who were Nazi weathermen in several of these bases over the course of the war. They learned, as I said, that their equipment was really not up to it. This is one of the men gathering mail on a nice day that was dropped out of an airplane to a base in East Greenland over here, that was right along the flight path to Iceland so that they could intercept the planes that came out of the sky. These planes did fall out of the sky, but men also died trying to attempt those rescues as their motorized transport didn't work well, their clothing wasn't warm enough, their boots weren't warm enough. So this led eventually to the establishment by the US military of something called the Snow, Ice, and Permafrost Research Establishment, first headquartered outside of Chicago, and led by this man, Henri Bader, who was a Swiss scientist trained in mineralogy as a geologist. But it wasn't a big leap for him to go to understanding the minerals to understanding ice, which is itself a mineral of frozen water. And there he is with a large ice crystal in his laboratory in Chicago. And what Bader did, and this is a picture, I'll play a short video for you. What Bader did after he got US citizenship was really lead and inspire the U.S. research program on snow and ice. And so this actually is his passport or his citizenship declaration. But he established camps on the ice, thought about delivery methods, tested or inspired people to test various means of transport, and most importantly, pioneered ice coring, starting actually in Alaska and the Juneau ice field on the Taku Glacier, and then moving to Greenland. The Alaska coring was 1950. The Greenland coring he started in 1956, and that was a picture of the 1956 or 57 coring at a place called Site 2, up ice from Camp Century in Northwest Greenland. And just about a year ago, the National Archives got back to a request I had made a long time ago for a radio program on which Bader was featured. And I'm just going to play you a little bit of that because it's a bit haunting. This man has been dead now for almost 30 years. To be able to hear his voice again as he describes ice sheets and why drilling in ice sheets is important. So you'll listen to him talk about that. At the same time, you'll see the drilling setup at Site 2 in Northwest Greenland as they're taking one of the ice cores there.
The purpose of deep ice coring is to get information on conditions deep down in the glacier. And since conditions are simplest on the high ice caps, this is where we have been drilling.
So can people confirm to me they actually can hear the audio that went with that? So make sure that's working.
That was fine for me. Thank you, Paul.
Beautiful. Thanks. I'll keep going then. Um, so Bader also realized that in order for people to work on the ice, they were going to need a dependable, if not comfortable, place to live. And so in 1953, the U.S. Army got creative with its ice cap housing, which in the past had been tents and portable vehicles and such things. Um, and they built two camps called Site 1 and Site 2, and they were built out of what some of the journalists at the time called massive sewer pipe. They weren't. They were steel bolted and riveted together, but they were large tubes, 16 feet across, 18 feet across, with risers on them so that as the snow accumulated, the tubes in the same way that a ballasted submarine would sink through the water. The idea was that these were supposed to sink through the snow and be buried by the snow. And as you can see in the top corner, there were hatches in which the men could get out and vents for the diesel generators that provided power. These were top secret when they went in. And this is a view from the inside in an Army released photograph that didn't come out until several years later. The tunnels were not heated, but the insulated buildings within the tunnels were heated. And this was talked about as weather stations on the ice, but in truth, you have to put them in the context of the Red Scares and the Cold War of the early to mid 1950s, where the Red Iceberg, which is North Korea, East Germany, Hungary, Poland, Russia, was coming to get the West. And another piece from the time, if Russia should win, American women will be crushed below the boots of Russian soldiers and such. Um, and these bases actually made it into the press. Of course, their location was secret. There were no maps, and they were described as weather stations. And this is a men's magazine from the 1950s on here. And the bases are described as we've built the military miracle in the Arctic, our secret base underneath the polar ice. And that's February 1955. But you can see from their cross section there that here are the men playing ping pong and sleeping in their bunks, and they're serviced by airplanes. And all of this was true from those stations, but they were only so secret in that we were, of course, advertising this to the world. The truth is that they were weather stations, and there are weather data still preserved from those stations, but their real purpose was as radar stations. And this is a photograph that you can find on the web today from a soldier who was stationed there at the radome that had the radar in it. And that radar was what's called a gap filler between some of the really big US military radars. And the stations lasted for 3 or 4 years and then they were abandoned. The interesting thing that I won't have time to talk about today is the Army went back until the mid 1960s and measured deformation in these tubes. And they hardly deformed. Over that period, they lost about a foot or a foot and a half in height and then expanded in width as they slowly squeezed. But they fared far better than the stations that the US built like Camp Century directly into the snow. So let's hop to Camp Century. That's the sort of ultimate under snow base. This is a map or a plan of Camp Century. The center trench is about 1,000 feet long. The trenches were cut into the snow and the fern with giant plows that had been used in the Alps of Europe, particularly Switzerland. There's a relation to Bader there for sure. And then they were covered with metal roofing material. Snow was sprayed back on them. It was allowed to sinter and harden, and then the metal forms were mostly taken out. The base was built with science labs and a research trench. That's where the drilling went on here. And it also was powered by a nuclear reactor. This is the nuclear reactor trench up here for several years of its existence. Building started in 59 and the base was abandoned in 66. The last people to walk in there were in 1969, and the deformation of the snow and the ice and the fern had almost completely crushed the base at that point. This is a French magazine, a magazine for young adults or teenagers, view of what Camp Century must have looked like. It's a sort of fantastical view, but it shows a lot of the major pieces in here. It shows the transport, over snow transport. It shows the nuclear reactor. It shows the heated bunk rooms the men lived in. It shows the excavation of trenches here and the roof forms being put on, and then the escape hatches. So you can see all the pieces that went in to Camp Century here from this particular piece of artwork. Um, the Army was really good at filming what it did, and these are some clips from some high resolution archival material we've gotten. One of them is going to show you the nuclear reactor being pulled across the ice by these giant D8 tractors. And the next one will show you what it's like in the camp, and I'll narrate a bit because they're not silent, but I have taken the sound out of them. So the nuclear power plant went in pieces and then was assembled once it got to Camp Century. Something like 300 tons of material that made up that nuclear reactor. And then this is the view down that main street soon after it was cut because you don't see a lot of frosting on the walls. Men, machines, supplies. And that nuclear reactor allowed them in these prefab shower rooms and bathrooms to have what the men describe as unlimited hot showers, the ability to brush your teeth and change your clothes and wash your clothes every night, um, and even to use an electric razor to shave and all those sorts of things. You probably should be wondering where did all the wastewater go? And it went into essentially large wells and sumps in the ice where millions of gallons of sewage sit frozen today. Camp Century was by no means secret. This was a almost bragging rights for the U.S. Army at the time. The cover of Popular Science, February 1960, is a color sketch or painting of Camp Century and the plows creating it. And these are the plows doing their job. Again, this great archival footage of the creation of the camp. They're blowing snow over the roofing material at that point. Inside, prefab heated bunk rooms kept at 70 degrees, heated floors in these things. Probably a little bit stuffy. They were not ventilated as far as I can tell, and there are many films and photos of multiple GIs smoking inside these. And rumors that the trenches didn't smell very good because the sewage disposal sumps were not very far away from some of these trenches. But they had full-on kitchen, unlimited frozen meat. They're cooking turkeys here in the dining hall. They served 4 meals a day, 1.5 times normal Army rations because the guys are working in the cold. But the thing that obviously people care the most about in this group and the legacy of Camp Century that is beyond everything else was the drilling trench. And this is a photograph of the drilling trench in color at the time. The top of the rig here just sort of poking out at that point. And this is most likely their drilling fluid, which was a mixture of Arctic diesel and trichloroethylene, kind of a nasty toxic mix that they used to keep the hole open in the last couple of years they were drilling. Took them 6 years to drill here. They drilled 3 holes. The first 2 were aborted. They were using an electrical drill at the beginning, and they kept having trouble with that. And then they switched to an electromechanical drill. And once they went to the electromechanical drill, they finished the hole in 2 summers and learned that that is probably, at least at the time, was the way to go for coring. So in 1966, the coring finished, and luckily one of the photographers is still alive, and I got to know who took a number of the photographs. This is one he sent me that it is in the book, and I have not been able to find it anywhere else. This is the Camp Century core coming off in 1965, and they would have loaded it into this oversized wagon at Camp Century. They were stacked vertically in here. And then these tires, which are taller than the average person by probably 50%, allow it to float as it's being dragged by the tractors across the ice for 138 miles. When it gets to the ice margin, a heavy piece of heavy machinery like this bulldozer picks it up and then drags it down the dirt road. And the cores were actually stored in a permafrost tunnel at Tudo, which was the base right at the edge of the ice where they were kept cold. Now, there's a great story that comes out of this. This is a photograph that I found just when I started doing the historical research, and the photograph really befuddled me. I was looking for this man in the center, a guy named Chester Langway, and I searched Google, and the first hit I got was a photograph of Chester Langway. It was this photo. Um, and it was on eBay, and I had never bought anything on eBay in my life, but I decided it was worth $4.99. And so I ordered up the photo. It was cropped fairly tightly. So you could see the men and you could see what I interpreted as ice cores there on the photo. And then having had the photo, um, started looking on newspapers.com, and it turns out that the same photo was published all over the United States with a great story that goes with it, which is Langway, who was the person who did a lot of the early analytical work on ice and then went on to run the U.S. Core Repository for about 20 years out of the University at Buffalo after leaving the Army Corps of Engineers. Langway had arranged to take the Corps to the Pentagon because, of course, it was the Army who were the people who funded this work. And that visit to the Pentagon was written up in these many newspapers. This happens to be the one out of the New York Times, which a particular sort of New York Times approach to it in the sense of saying, starts off with, what would you expect a soft drink cooled with ice formed 2,000 years ago to taste like? And what Langway did is took chunks of the core, put them in these paper Dixie cups you could see here, presumably took this microphone, put it over the cup, and in the Dixie cups was Coca-Cola, and you could hear the bubbles that were under pressure in the ice pop as it melted in the Coca-Cola. And so the report from the New York Times is the Coca-Cola drink tasted like Coca-Cola, and the ice taken from the 1,800-foot level and said to have been formed about the time Christ was born tasted like ice. So big splash, end of this project. And then several years later, this paper appears, which I'm guessing is familiar to most people in the audience. This is the first long stable isotope record of climate from an ice sheet, and it's Willie Dansgaard's work. He had the only lab at the time capable of processing the huge numbers of samples, thousands of samples it took to do this. And this is the result. As a function of depth on this axis or of time from an ice flow model on this axis, and the Holocene here, and then the last glacial maximum, and the descent into the last glacial maximum, and then presumably ice from the last interglacial. And the time scale is a little bit off, but it's not off by very much, which is a testament to what these folks did many decades ago. And so their focus was on the ice. Most of the rest of the work on the Camp Century core was on the ice. And this sub-ice sediment, for which they have collected about 3.5 meters, was really largely ignored. This is a photograph at the time of Langway and Lyle B. Hansen, the driller. This is the sub-ice core, a piece of the sub-ice core here. In front is some of the basal silty ice core here. It's been cropped off by the photographer. There were three papers published, 70s and 80s about this. One found some biological material, but there were diatoms, nothing about plants in the core. Another one looked at the shapes of the grains in the core, and another one looked at the petrology of the rocks in the core. And then the core vanished. It was last seen in the United States in the early 1990s. The rumors were they had gone to Copenhagen, but there was no confirmation of that. And many people gave the sub-ice core and the lower part of the Camp Century core up for lost at that point, which I think for many folks at that point was not, in a sense, a huge loss because we had many new ice cores that were attracting attention. In 2019, I got an email from Dorte Dahl Jensen in Copenhagen asking me to come to a meeting to talk about old ice and the bottom of ice cores. And when I got there, and it was April, we had a day of meetings and talking, and then we went into their brand new ice core facility that hadn't even all been put together at that point. All the crates of ice were on the floor and the shelving was being built. And JP Stephenson took us to the back and showed us the Camp Century sub-ice core. And these are photographs of the day, the minute basically we first saw it. It was probably plus 20, plus 25 outside, and I think it was minus 27 inside at that point. And this is several of us looking in astonishment. That's Jörg Schaefer. That's myself, obviously not dressed well enough for being in the freezer for very long. Looking at the pieces of the sub-ice core, and you can see they're in battered cardboard boxes like this. Turns out those are some of the original boxes from the ice core lab in Buffalo. The stickers and the names are still on there. So the ice core had been transferred from Buffalo in the mid 1990s when the rest of the U.S. collection was transferred to Denver. The Camp Century core, the Bird Station core, and the sub-ice material was all transferred to Copenhagen, where it's been stored safely since. These are three women who've been working with us on this project. Kat, Hallie, and Juliana, they're all finishing up. Well, Kat's finished her master's, and Hallie and Juliana are now finishing their master's at the University of Vermont. And they're with that original box. So the Danes shipped to us two pilot samples, and that was in 2019 in the summer. And 4 months later, we had a kickoff meeting in Vermont with about 40 people where we had taken that material and distributed it to a number of scientists around the world. And then we all got back together a couple months later and talked about the data. This is the uppermost sample in the sub-ice core. And you can see there are some sub-rounded grains here. There's a bit of stratigraphy and a bit of layering in here. There's a lot of coarse material in there. And so the first thing we did after photographing this was to melt it. Actually, the first thing we did was to put it back in a fume hood before we put it back in the freezer because it stunk so much of diesel fuel and trichloroethylene. We melted it in the hood overnight, and then we sieved the material to grain sizes so that different scientists could have different grain sizes. And because we had so little of it, just a couple 100 grams each, these are pieces with an archive half left in Copenhagen. We kept everything. We filtered all the water. We tried to lose not a gram of this material. And this is a short video of Drew actually filtering the water here. And as that was filtering, I was sort of absentmindedly staring into this bin and noticed these small things floating at the surface. And the only way that I knew what those were is I'd had a prior part of my career where I worked a lot on lake sediment cores. And whenever we wanted to find material to radiocarbon date, we would put it in a bin of water, stir it, let it sit for an hour, and see what floated to the top. And so on this hot July day, I remember turning to Drew and saying, I think there are fossils in these samples. And Drew turned back to me and said, you're crazy. There can't be fossils in sediment from the bottom of the ice sheet. And it turned out that that was a bit of providence or luck or history that I'd had that allowed me to recognize those for what they were. This is a view down that Buchner funnel with filter paper on it. And the green arrows are going to point to the material that indeed were small fossil pieces or subfossils or macrofossils more properly. These are organic material, mosses, small twigs, pieces of leaves, bits of insects, and there were thousands of them. And so that led to the first paper that Drew led. And there's that same photograph I showed you in black and white earlier. And we had an initial stratigraphy, thanks to work by Piache and Jean-Louis, who had done the initial logging of the core materials before they had been cut. And then, of course, we had the photographs of the two core materials. The Danes had given us the absolute bottom, and they had given us the top. And the idea was to bracket this material so that we knew what was analytically possible. We had no idea that anything particularly interesting would come out of this. The goal was to say, we got the top and the bottom. Let's see what's detectable. And then when we have some data, write a proposal, get some funds, and do it right. Well, it turned out that the data were absolutely fascinating from both of these. We collected the pore water, and so if we look up at the top here, these are the pore water major ions. And you'll notice that the red is the lowermost sample here. The blue is the uppermost sample. And you'll see that there are far more dissolved ions in the pore water in the lower sample than they are in the upper sample. And that was our first clue that this lower sample must have had a lot of contact time with water in order for those concentrations of calcium, magnesium, sodium, and the anions to be so high. Then we put the samples under the electron microscope, and the story continued to be the same. The lower sample, we have mineral, this is a pyroxene here, but you can see the coatings on the side. These are clay coatings around the grains. Most likely this reflects a long period of soil formation, of petagenesis, where the minerals have been altered, and the water in there was leaching cations and anions, and that ties back to the high concentrations in the pore water here, which of course was frozen until we melted it. If we look at the uppermost sample, there are really no grain coatings on here. They've been stripped clean. And that implies transport. And it also explains shorter residence times where there are far fewer major ions in here. And if you just look at the two samples, the bottom one looks like a hand sample of till you might cut out of an outcrop on the landscape. The upper one looks like material that's been moved by moving water, fluvial system, a river, a stream. And then the last piece of data we had were beryllium and aluminum, cosmogenic beryllium and aluminum 10 and 26 measurements. And without going deeply into the system, these are two cosmogenic nuclides with different half-lives. They were measured in the sand fraction as well as the coarse fraction, actually in three different fractions. One was the sort of freezer burn material that had fallen off the outside. And so these are essentially replicate measurements you're seeing here. And those replicate measurements clustered really nicely. And what we can do with that, because these nuclides have different half-lives, is we can say from a diagram like this, which plots the ratio versus the concentration, we can say the amount of time that the sample, or a limit on the amount of time since the sample was last exposed is the best way to put it. So we know that this upper material could not have been buried any more than about 1 million years, because if it had been, the ratio would be lower. And we can say the lower material could not have been buried more than about 3 million years, or else the ratio would have been lower. So from these two samples, we had an initial feeling that we were looking at material that most likely had been exposed at some point in the Pleistocene, and all we had were limits at that point. This couldn't have been buried for more than 1.1 million. This couldn't have been buried for more than about 3. But we knew that there was a really interesting story here because there was a stratigraphy, there was geochemistry data, there were fossil pieces of fossil material of a fossil ecosystem in here. And that was enough to get the US National Science Foundation and reviewers who read the proposal interested enough that we could scale up to looking at the whole archive. So indeed, we got funded to do that. And Drew, who was again the postdoc at the time, went to Copenhagen, worked with Jean-Louis and Pioche and JP and the staff there. And they cut 28 additional samples, leaving the archive house in Copenhagen. I have a short video of that cutting here for you. This is the archive or the storage facility once all the shelves have been up. And then they stayed in red light to do much of the cutting. Good. And the purpose of the red light is so that we can do optically stimulated luminescence measurements, which will give the timing of last exposure to sunlight. And so you'll see this one is being done in red light. This is quite dark. That's Pioche assisting with the cutting. We used both a bandsaw and a diamond saw to do this, depending on the pieces. And Drew had worked out a very intricate cutting approach that resulted in a number of small pieces that were used for different analyses. And that's what it looks like in the red light. In daylight, this is one of the deep samples, and this is what we now interpret as a basal till, a dimict. Some rounded class, but mostly angular class in a matrix that's not class supported, it's matrix supported. He brought that back on a direct flight from Copenhagen to the United States, and then immediately made some paleomagnetic measurements in New Jersey, and then brought about 17 kilograms of samples back to the University of Vermont, where we then processed them and distributed them to the working team. At this point, I really have to say a huge thanks to two men who are responsible for this core still being extant and is in such good shape as it is. The first is Chester Langway, who watched over this core during its time at Krell and then during its time at Buffalo. And then JP Stevenson and the group in Copenhagen and their ice core storage lab that has kept this core safe ever since then. And I think what's impressive to watch or look at is on the left side is the Camp Century subglacial sediment published in 1981. It's before the core was cut into pieces. The core was cut into pieces in 1972, and you can see the whole run of samples here. You can see the run of samples here. The numbers correspond to the tubes in which the samples were kept. This is the top, and this is the bottom. What Drew did is took a number of photographs so he could recreate three-dimensional views of these core segments. And with those, he could recreate where they were located exactly, check to make sure that they hadn't been inverted. In fact, several of them had been inverted during storage. And he could see the samples that were thawed, and he could determine that there were 2 missing samples in here. So pretty good record for a core in 1966 that there are only 2 missing samples here. One's been thawed, one was refrozen on there, and several they didn't have sufficient sample to make a 3D model like this. But amazing preservation of a really old core. So this is the cryosphere paper. I won't take you through all of the gory details in here. You can read them for yourself, but I just want to point out that there are more than 20 institutions. I think we've counted now 5 countries represented, 35 scientists, 7 graduate students working on this core. This is the first paper we've had out as a group, and it really is the methodological paper and the basic data. So here are the photographs of the core from different times. Here are the core designations. These were given by Langway as the core was cut up. What's happened to the core, what's been sampled, things that might be missing, a basic stratigraphic log with grain size, then grain size distribution based on our melting all the samples. And you'll notice that there's an upper unit. We've broken it actually into 3 units. The first 2 up here are water washed. The third one is most likely a slump or debris flow. Then there's an ice-rich unit in the center, which remains a bit of an enigma. And then there's the lower unit, which is a dimict or till. We have measured the cosmogenic in situ beryllium-10, which is actually quite revealing. It shows us absolutely nothing in the deep till unit here, which in itself is really important because if this had been exposed near the surface, we would see a depth profile similar to what we see above. We don't see that. So that means that this surface was never exposed to cosmic radiation at Earth's surface. It may have been exposed at depth, but not at Earth's surface. Whereas the upper material absolutely has been out and exposed. It also confirms the idea that this might be a small slump or debris flow because cosmogenically it looks very much like what's below. It also looks similar geochemically. We have stable water isotopes of the pore ice. I'm not going to go into those. That could take half this talk to explain what we think might be going on here. We have pore ice pH. Very telling are the dissolved cation concentrations. I already started on that, where we have high concentrations of dissolved cations in the lower material, lower concentrations, or so I should say intermediate concentrations in the upper material, and this intermediate ice layer has very low concentrations. And I'll just give you a clue that our thinking at this point is this is either leftover basal ice or firn that was in place and then buried by a shallow stream moving that sediment. We also have a lot of organic geochemistry data, which at this point is also a bit perplexing as to what exactly it means. I want to show you a little bit about what Kat Collins did. So Kat did a lot of electron microscope work, but I think the thing that she did that will have the most long-lasting impact is doing micro CT scans of each of the sections of core before we melted it. So this provides an archive for the future for people to see what these sections look like and their grain sizes, their stratigraphy. Typically, when you melt this, it's gone. But in a sense, we have these wonderful memories digitally now, down to about a 70 micron resolution on here. And what Kat is doing here in this video that she made is going from the top down. So we're actually at 1060 right now. We're in this section here. And then you'll see as these get peeled away that we've now moved into the debris flow at the bottom of 1060 here. Probably originating from the till or the dimict. Geochemically, it's very similar. And then go through the ice layer once we get out of this till, and then we'll go into the till down below. So 1061 is part of that ice layer. Some of these are actually small bits of sand and pebbles, but much of these are clots of material that are fine grain and have been ripped up and are in that ice layer in here, which is consistent with this being potentially basal ice. And now we're back onto 1062 here. We're back into the lower dimict, and you can see that this looks a lot like tills that you may have seen in the field, again, with large class. So I encourage you to have a look at this paper and to see what she's did. And all of these videos are online in an electronic repository, and you can look at them. See if I can move forward. There we go. So the next paper that came out was in 2023. This is work of Tammy Rittenhauer in large part and her luminescence lab in Utah. And Andrew Christ was again the first author. And we sampled, again, those 2 pilot samples. We cut samples for luminescence from the inside of the sample. And the rationale for doing that is that was shielded from light. So even though the sample was left out in the daylight, the center part, because of the absorption of the sediment in the rock, was not. And I'm trying to get this video to play, which seems to be a little cranky. Yep. Let's see. There it goes. Um, well, I guess we're not going to get that video today. But what this is a creation of Drew's that rotates that sample for you. But we collected the luminescent sample from the center, and the data that we published in that first paper in Science here is 416,000 years ago, plus or minus 38. Hawk, who's a master's student at Utah, who's just finished up, did dating on three more samples going down in the upper fluvial unit and into this debris unit here, slump unit. And you notice the dates are all consistent, 417, 422, and 414. So now we have replication of that initial date, and we know pretty much for sure that the deglaciation of northwestern Greenland was indeed during MIS 11, um, and implies that at least that corner of Greenland lost almost 1.5 kilometers of ice at MIS 11, 400,000 years ago. Hallie Mastro, who was the other master student I introduced you to, has been working through the fossils. She's almost finished at this point. She's been working with Dorothy Petit and Ola Benecke to type these fossils. I'm just going to show you a few of these. I am absolutely not a botanist. That's a Hallie thing. There's a picture of her working on the microscope. She spent much of the last 2 years staring at a microscope. But these are some of the things she found, and you'll notice the units light up here as I show you this. The upper one is poppy seed, and I think this is a wonderful graphic she's created where you see the fossil and then you see what it would look like today if you saw that in the field. So this is a sedge here, and you can see the sedge seed there, and then you can see the sedge there. And you can see other things. This one I put up because this is a midge fragment here. There's the midge today. There's the fragments that we find in the sediment there. So we really, with Hallie's work, have the ability to recreate what the ecosystem was like when the ice was gone in Northwest Greenland, and to a much more limited extent at KISP2. Ben Kiesling did the modeling work to try to constrain if Camp Century was clear of ice, what are the possibilities for melt on the rest of the Greenland ice sheet? And his conclusion is that you can lose anywhere from about 1.4 meters of sea level equivalent from Greenland to up over 6 meters of sea level equivalent from Greenland. So Camp Century is non-determinate in that fact. It tells us that at least 1.4 meters of the sea level budget comes when we melt the ice off of Camp Century, but it also allows for 5 or 6 meters of the sea level budget, which makes understanding what's going on at GISP2 that much more important. So let's look at that 416,000 year age for a bit and what that tells us. From the luminescence dating, we know that that upper sample last saw sunlight 416,000 years ago. We also know that MIS 11 is a long, warm interglacial. Global temperatures at the time were probably about where we are today, between 1 and 2 degrees Celsius above background. Carbon dioxide was at 286. Sea level by the end of MIS 11 was 6 to 13 meters higher than today. So low eccentricity, high obliquity, weak precision time precession time in terms of orbital forcing. And its claim to fame is being a really long interglacial on the order of 30,000 years. And you can see that by looking at the CO2 record here, a long, broad peak compared to 9 or 7 or 5e on here. Same long peak of methane as you had of carbon dioxide, and in the stable isotope records, the same thing. So perhaps in many ways, it's not unsurprising that if Greenland were to melt, it would have melted at MS11 because the time for melting was long. And we know that there's a lot of, of thermal and basically kinetic inertia in melting that much ice. And, of course, there are people much smarter than me who've published on that. And so, our work, I think, is consistent with what others have been thinking. And this is Drew's slide, and I really like his analog here as this is an imperfect analog for the future. But certainly it's the equivalent, as Drew would say, if you leave a freezer open for a long time, the ice in it's going to melt. And with Earth here, instead of the freezer, and this happens to be a picture from the Army at Thule in the 1960s, where it snowed so hard that the doors to the barracks were covered in snow, and so the men made use of them to cool beverages. But instead of warm drinks, if we leave the Earth warm for a long time, we're going to get high sea level. And the frightening thing to me when I look at this is we are headed right now to at least a moderate, if not a high emission scenario. And these are some of the representative concentration pathways for emissions. And if you look at that, the time it takes naturally to return, even under moderate emission scenarios, the time it takes to return to background CO2 is on the order of tens of thousands of years. So in that case, maybe MIS 11 is not a bad view at what we are doing to the Earth now, unless we change our ways and can get that carbon out of the atmosphere. And of course, we can look at Andrew Dunton's work on sea level that suggests 6 to 9 meters at MIS 5E. There's no indication that the ice left Camp Century at 5E. 6 to 13 at MIS 11, and her suggestion that maybe three-quarters of the Greenland ice sheet was gone at that point. So let's flip over to GISP 2 to finish up. And this core was finished in 1993. And again, it's summit location right here. And Mark Twickler sent me some drilling footage from that he had pretty clearly captured on a VHS recorder at the time. Very different than the drilling, of course, at Camp Century. They're using a butyl acetate, and they're taking way better precautions for their health with that drilling fluid. And when they got to the bottom, they were able to core about 1.55 meters of basal material. And there's a little bit of confusion in the early literature. The entire packet we now know is 1.55 for measuring what is in the core repository. But they describe that packet as erratic boulders, then about 8 centimeters of till, and then the rest they call bedrock. I prefer to refer to it simply as rock, in that I've seen perhaps too many meter scale erratic boulders in my life, but it's certainly a similar lithology here. The erratic boulders are different lithologies than what's below. And Jörg Schaefer and others, and this is a photograph from the Ice Core Lab that's used in their paper that I've colorized, measured aluminum 26 and beryllium 10 in these rock samples. They combined some of these rock samples. So this is an erratic, this is an erratic, this is an erratic. We studied the till, this yellow here. You can see the centimeter scale there. Then this is the rock below, rock below, rock below, rock below, rock below, rock below. And Schaefer, in order to increase their measurement precision, combined some pieces. So they combine these two pieces, single piece, combine these, this one. And then they combine these two pieces, which it turns out are an erratic and the rock below with the till in between. When we got to till, our intent was to measure the cosmogenic nuclides, and we did, and they actually agree pretty well with Schaefer's measurements at lower precision, but they agree well. But the real surprise in the till, and these are photographs of the till from Deb Meese, who still had them in her archives after all these years. There's the till itself here, and there's a clast in the till right there, and then there's a little bit more till below the clast. This would be that erratic above, right here. This would be the rock below, right here. Second view from the other side with much poorer lighting of the till, and this can make you believe it's till. These are angular clasts in here. There's that large clast. There's a little bit more till. This is down, and this is up. So the till was maintained frozen for at least about 9 months, and we don't know how much longer. And then it was thawed, dried, and sent for isotope and fissure track analysis. So we got till that for the better part of 30 years had been kept dry, and we had no thought that there would be anything organic preserved in this. But we were really wrong. We sieved this out, and immediately upon sieving it out, we found what I showed you in the beginning: soil fungus, megaspores, poppy seeds. So that organic material had survived almost 30 years of being warm and dry and out of a freezer and non-refrigerated, and was in actually quite good shape. And so Hallie did the same thing she did at Camp Century here for GISP 2. She identified these are the spike moss spores, these are spike moss, there's the poppy seed, there's the Arctic poppy. And this is Arctic willow, a piece of wood. This is working with Barry Rock at the University of New Hampshire, who does SEM analysis of wood. And the way the vascular structure in this wood lines under the electron microscope shows that it's this Arctic willow, basically a tiny shrub that you can kick along the ground here. And together, the botanists on this paper all agree that this was most likely a rocky, dry ecosystem at GISP-2 that might have looked something like this. This is from Brunevik in northwest Greenland. As of the moment, the only age we have on this is Jorg's calculations based on the aluminum and beryllium data there, less than 1.1 million years. So what we know now from Jorg's data is that GISP-2 was free of ice less than 1.1 million years ago, and when it was free, it was occupied by a dry, hardy tundra ecosystem. So to wrap all this up, we know from the Camp Century core that Greenland's ice melted naturally at less than 300 ppm carbon dioxide in the atmosphere. And yet, if that's the record from Epica and Vostok here that shows the carbon dioxide levels. 1950 level here, this is when the subice sediment in Greenland we know was exposed to the sunlight. Levels in our atmosphere from here up to here. As of this summer, when I made this slide, we were at 423 parts per million. So about 50% more than we were when the ice left Northwest Greenland. And so we know now that Greenland was at least 90, probably 95% ice-free within the last 1.1 million years, at CO2 levels that were at least 30% less than they are today, perhaps more. And I think that lends support to what some people would call the fragile Greenland hypothesis. And so it's picture Wally Broker here, and Wally's famous for saying climate is an angry beast and we're all poking it at it with sticks. And I would replace climate at this point with Greenland is an angry beast and we're poking at it with sticks. And just to put a little context in this, if you look back at Life magazine, for those of you who aren't American, this is a really popular magazine through the 60s and 70s, large format with photographs and lots of advertisements. If you go to 1962, you'll see this advertisement from Humble Oil, which was a predecessor, was absorbed by Enco, which was absorbed by, anyway, ended up to be part of Exxon. And with SO in between. And if you can't read this, I'll just read it for you. It says, each day, Humble supplies enough energy to melt 7 million tons of glacier. The giant glacier has remained unmelted for centuries, yet petroleum energy Humble supplies, if converted to heat, could melt it at a rate of 80 tons each second with an exclamation point. So in 1962, it was bragging rights that fossil fuels were melting glacial ice. It is no more, clearly. Also in February 1960, futurists were looking at what was going on in Camp Century. This is a fellow who drew comics every week for 5 or 6 years for the Sunday papers in the United States. And he drew this particular comic. It was called Closer Than We Think. And it's entitled Cities Under the Ice. And it says, ice caps no longer prevent people from inhabiting the frozen wastes of polar regions. In fact, ice itself may become a shelter for future settlements. And, you know, he had nuclear power plants and fancy cars and fancy train lines and solid ice above and ventilation and all that. Of course, this never came to pass either. So I just want to finish by saying that the power of this basal material is in some ways it's the fact that it's actually not ice, and it so records something very different than the ice. And it lets us see the surface processes that were active when the ice was gone. It has a stratigraphy and a layering that we can deduce and that we can use to understand those surface processes. It has pore water within the grains of those sediments that allows us to understand weathering processes and soil formation processes and processes of the biosphere and organic acids and things that exist in their organic molecules. It allows us to look at soil development by doing things like soil color and soil texture. And it allows us to understand its structure with Kat here during COVID, doing CT scans. And it allows us to see the ecosystem that once existed, including seeds and including other fossils. And I think particularly important, it allows us to date using luminescence the last time this material saw the sun. And if it can see the sun, it means that the ice wasn't there. So to me, it's a bit of a paradigm shift from thinking about ice cores as only reflecting the ice and maybe the basal ice or the silty ice, to ice cores and the basal cores below the ice cores reflecting what the land was like when the ice was not there. So I'm going to stop and just give you these particular resources if you're interested in more of this. The first one is our website for the project that has all of the science we've done, the people involved, and some historical materials. The second one is my website if you want to find out some more of what I've been doing. The third one is our laboratory where we do beryllium-10 and aluminum-26 at the University of Vermont. That's supported by the U.S. National Science Foundation, and we are supported to have visitors. And the last website is for the book if you're interested in a popular view on this. And at that point, I'm going to stop and take questions from folks.
Thank you very much, Paul, for a wonderful and very wide-ranging talk. Martin's just put an amusing comment onto the chat, which is that the Humble Glacier is actually Taku Glacier,
That's
which I didn't know. I've seen the advert before, but I'd never seen that before.
that's
So thank you
fascinating. I
very
did not
much.
know that either. So thank you, because that's of course the first place Bader drilled. So that's a great thing to know.
Um, We normally ask people to just type onto the chat to say that they've got a question to ask, and then get people to unmute and ask their question properly. Does anyone have a question to ask? Maybe I'm not looking at the bottom of the chat. Anyone? Roger, do you want to unmute yourself and go ahead?
Yep. Thanks very much, Toby, and thank you, Paul. That was tremendous fun. Just a quick question: were there any physical property measurements made of this core before it all got melted and so on? I'm thinking density, possibly P wave speed.
We don't have P wave speed. We do have density in two different ways. Piache and Jean-Louis measured density, I think, by total estimated volume and mass. And then we did it again as we melted the material. And we also have, percent water. P wave speed, no, but the archive halves are still in Copenhagen.
Hmm.
So the purpose of this was not to destroy anything so that someone couldn't make more measurements. So that's why the archive halves. So those are there, and I assume you could measure P wave speeds in them.
Yeah, that would be fun because I remember Nana Carlson's paper with the GPR to
Mhm.
relatively shallow depth, but actually having a measured bed interface would give those of us interested in the seismology and the reflectivity, the seismology, something that will tell us what the answer is instead of us trying to figure it out.
Oh, that's a
Calibrating everything.
fascinating. I don't. How much do you think things could have changed in 50
Yeah.
plus years of storage? Uh,
Um, well, the fact that there's a clear ice, then this bed
mhm.
means we have an idea of there wasn't a thin melted wet layer there and so on and so forth, and us seismologists are always looking to calibrate our reflectivity information and try and use it to characterize what's under any other ice sheets, and there's
Yeah, I
lots
know.
of
I think we have to suppose this is cold based now, and it had to have stayed cold based, or else this rather fragile material would probably not be sitting there for us to sample.
mm,
Uh, we don't know how much is gone, so that's a question. We know we've got MIS 11 there. Could there have been another period of exposure and that material's eroded? I don't think we can rule that out. Um,
mm,
and there doesn't seem to be much disturbance of these. You can look at the CT scans. There is some cracking and water filling of those cracks, which is indicative of permafrost. And we have not yet, but are working with some of the folks at Colorado to try to do the sort of 3D spatial analysis of those cracks and see if that reflects any type of sort of preferential stress field. That's in the future. And again, those CT scans are great. The problem is, though, that when they drilled this, it was not done with aligned drilling, so we don't know exactly how to match up those four different sections
mm.
rotationally. You can do some of it visually, but it wasn't preserved that way and wasn't drilled that way.
Yeah, but it's a better glimpse of ground truth than we usually get when we're shooting our deep seismic and then just waving our arms and trying to measure amplitudes and stuff.
No,
So
very true, very true.
yeah, thanks very much. That was tremendous fun, especially seeing a B-29 on the ice sheet.
Kerim, do you want to unmute yourself and ask your question?
Yes, hi. Fantastic talk, especially the historical perspective. I mean, that's an incredible work that you've collected there for all of us coming after. I had the question because I'm trying to get my head around the sea level estimates. You know, which cores that you actually found the evidence of no ice or when the ice was gone, and then using that to backtrack with like Ben's work to get the ice volume. So you're most focused on Camp Century. You also mentioned GISP 2. There's also Northeast Greenland, you know, those well like East Grip and others that haven't been as well. We haven't had that type of basal sediments or a material yet. But what you need to actually pin this down, and what sites can you just summarize? Have you actually got this evidence of the date when it was gone last time?
Sure. So really, we only have evidence for two sites. We have a Camp Century, which is, I would say, the best dated right now because of the luminescence ages at the top. So we have a firm MIS 11 age. Ben can explain to you the modeling far better than I can. That's
Yeah,
not my expertise. I'm a glacial geologist,
I'll be
geochemist.
asking him anyway. I know he's not online, but yeah.
Um, so his estimate, of course, is very broad, and that shows the lack of sensitivity of that northwest corner. And so GISP 2, and I take the 95% from the figure that's in Jorg's paper, the 2016 Nature paper. Um, GISP 2, we only have a limiting age right now. We have the less than 1.1 million, and we don't know how much less. It does not preclude 400,000. That could
Mhm.
be MIS 11 too, but we don't have confirmative data. We just have a limit.
Right.
There are other data consistent with that being 400,000, but they don't mandate it either. You can reanalyze the data that Jorg took with the cosmogenic nuclides and the data we have, change some of the assumptions, and you can expose that 400,000 years ago for a single exposure. But again, it's a non-unique solution, and that's part of the problem of working with these cosmogenic nuclides is we measure the final outcome, but we don't know the path.
Mm.
And, and so, we can set limits, and that's about all we can do. So
Right.
to me, the most important thing would be to get materials from places like GISP to other places in central Greenland that can be dated with luminescence. And there's a
Right.
discussion running around my email and other people's emails about getting back into the GISP 2 hole and redrilling that because there's the first time we went down, we came back with till. That's no guarantee that the second time you go down and drill 10 meters away, you're going to get that same till, but the potential is there.
Right.
And the Green Drill project that Jorg and Jason Briner are leading in northern Greenland has brought sediments up. Those are very marginal, though. So that will tell us a lot about what the ice margin is doing, but it won't tell us about the major volumetric changes in the center of the ice sheet.
Right.
So if you had to ask me, we need holes in the center of the ice sheet that represent the places where if the ice is gone, and they have to be cold based so that they can preserve the record of that, we could potentially date when it was gone. And I think that's, the data we have are wonderful and they're interesting and they're cool. I think the real takeaway from this is that getting to these basal materials can tell us a history of the ice sheet that goes much farther back than we're ever going to get in the ice. And
Mm.
that's in 10 years or 15 years, if someone looks back at this project and what the 40 of us have done, I hope is to have catalyzed people looking at the subglacial materials.
Right.
And
Yeah.
and then to reflect on your comment on history, it's pretty amazing that Bader and Hansen thought it was important enough to not stop when they got to the bottom of the ice, but to keep going. And Ueda claims, who was the lead driller, he claims if they hadn't have burned out a bearing, they would have kept drilling
Mhm.
even further. So, to me, that I was 5 years old when these guys finished this core, and I'm kind of old now. So that's amazing foresight to think that their brains were working that way in
I know
1960.
there's some other East Group and other core people on board here who are listening in carefully on what you're saying there because, yep, exactly that is happening again, right? Preserving everything, you never know what we can use it for later.
Exactly, exactly.
Yeah, I think it's a wonderful indication of the importance of keeping all those field notebooks and all the data and everything.
Well, and that's just a really big shout out to the people who run these ice core facilities and keep these cores frozen and keep the data.
We seem to be dwindling numbers here, Paul. So I think unless anyone's got a burning question, we should probably close the discussion so uh, people can get back to their various commitments. But thank you so much. That's been absolutely cracking talk to open the series with.
No,
Really,
thanks.
really varied and just fascinating. So thank you very much indeed. Really appreciate it.
Thank you for having me.